Hi everybody, my name is Nicholas Peabody and I'm an applications engineer at Texas Instruments in Santa Clara. In this webinar, I'm going to be going over the topic of implementing a PCIe redriver to reduce design complexity. I will be discussing three main topics. First, I will explain the sources of loss inherent to a PCIe system and discuss a way to counteract that loss. I will then continue to discuss the definition of a redriver with information about the package and configuration, as well as giving a comparison with retimers. In the end, I will provide the available TI solutions and give a suggestion for high-speed modeling using IBIS AMI. In many PCIe systems, copper transmission media like cabled systems, backplanes, midplanes, and switches are used to connect peripheral components to the central processing unit, or CPU. For example, a solid-state drive, or SSD, will store data from the computer in the form of accessible memory that the CPU can utilize to perform necessary operations. In this case, it is very important that the SSD can send data to the CPU, and that the CPU can send data to the SSD. If the data were corrupted, that could deal a critical blow to the system. In this case, the issue lies in the fact that copper transmission media leads to frequency-dependent losses to I width and I height, shown by bit errors or incorrect information being seen at the receiver. However, there is a solution to this problem in the form of signal conditioning components called redrivers. Redrivers apply EQ boost, which can offset the low-pass filter characteristic of copper transmission media. As is shown on the figure on the right, the various gain settings of the redriver can compensate for losses. The graph on the right shows the boost profile for our Gen 5 redriver. Each EQ setting from 0 to 19 that our redriver can assume has a target frequency at around the Gen 5 Nyquist frequency of 16 GHz. As you can see, the peaks of the gain curves are around 16 GHz. The question becomes then, how to implement a redriver in a copper cabled system. The image on the left shows the summation of a system which utilizes a redriver. The first graph shows the losses you might expect from copper transmission media. This is a common insertion loss profile. See how as frequency increases, the decibel loss on the channel increases linearly. This means that at higher frequencies, the data is going to be further attenuated. The middle and third plots show how a high-pass filter can counteract this effect. Notice how the middle plot has a high-pass filter characteristic. This means that at higher frequencies, the data is going to be boosted. The third plot, notice how the resulting data is not attenuated for the beginning and mid ranges of frequencies, and only starts attenuating once the high-pass filter reaches its peak at around 16 GHz, which is the Nyquist frequency for Gen 5. Redrivers boost the high-frequency components in the signal with this method. Redrivers come with different packages, sizes, and configuration options. The packages we use are QFN and BGA. Depending on the number of channels that the redriver has, the package will be different. Our BGA package is used for our 16-lane Gen 5 device, and the QFN packages are used in our 4-channel and 8-channel devices. For reference, the area of the redriver is less than 50 millimeters squared. To simplify operation, our redrivers use the concept of an EQ index. Every index is a combination of 3 amplifier settings, ordered by their total effective boost strength at Nyquist frequency. For example, EQ boost 1 boosts the most at Nyquist frequency, whereas the second order EQ boost 1 will boost less around the Nyquist frequency. So, the index number can be thought of as a whole device boost strength setting with 21 options. For most customer projects, configuring the device by EQ indexes is sufficient. Next is the output driver, which is a simple differential amplifier that does not apply frequency boost. It controls the DC gain, which is the redriver's second tool for signal modification and comes with 5 options. The output driver can make the signal larger in voltage at the cost of increased noise, or smaller in voltage for reduced noise. Finally, there's RxDetect, which is a required function by PCIe specifications for startup sequencing. It's the only self-driven or smart behavior the redriver has. In the next slide, I'm going to go over an application in which a redriver can be utilized. Additionally, in terms of communication with the redriver, there are a couple available options. One is using pin mode, which would mean that the redriver settings will be configured by the input voltage to the pin. Say, for example, if you wanted to set EQ0 or EQ1 using pin mode, you could use the appropriate resistor value to set to the appropriate level which you want to set to, as is designated in the table in the datasheet. The other would be using SM bus mode. This form of communication also enables reading and writing to the device's internal registers to obtain status updates on RxDetect or other functionalities. If you're interested in either of these modes of communication, see the DS320 PR410 datasheet and DS320 PR410 EVM User's Guide and Programming Guides for more information. Finally, please pay attention to the voltage supply input to the redriver at VCC. Notice how the redriver needs a single decoupled 3.3 volt supply. In this case, the device's internal voltage regulator provides immunity to supply noise. Redrivers are tuned by setting the various EQ indices to counteract the system loss. Often, the CPU uses PCIe protocol to transfer information over PCB traces to appropriate generation SSD arrays. In the diagram on the left, we see a common architecture used in PCIe enterprise systems. See how the CPU is separated from the SSD array by a riser card and a cable. The amount of loss from those cable interconnects and long PCB traces on the riser card will need to be compensated for. And the EQ indices we discussed earlier are a good tool to help. Imagine you are communicating with a friend across the distance of a very large room. Because of the distance between you and your friend, you will need a method of passing on your information, or else the information may be lost as the sound of your voice is attenuated over the great distance. In this case, and in the case of signal communication, there is loss along the line of transmission. A repeater is like having another friend in the middle of the communication line who can help forward your message by applying a boost to the information. But what if the loss is too large? In certain cases, a redriver's boost will not be sufficient to relay the correct information. In those cases, it makes sense to use a more complex and robust form of signal conditioning in the form of a retimer. Retimers are more complex and have more signal conditioning tools than redrivers. The ability to set EQ indices with the CTLE block is there, but new signal conditioning features include a clock and data recovery block, a decision feedback equalization block, buffers, serial deserializers, and other digital systems. The additional forms of signal conditioning compensate for losses that the redriver cannot compensate for. However, the strong capabilities of a retimer come at a price. Retimers need a PCIe clock input, whereas a redriver just ignores the clock. A retimer needs separate digital and analog power rails, and the digital supply must be high quality, whereas the redriver only requires a single supply. Additionally, a retimer will very often need additional programming and temperature control. As a consequence of high power consumption, a heatsink is usually required. Finally, there are lots of settings to configure the link before linkup can be initiated, so an external EEPROM is typically used with a retimer. In small, low-power systems, redrivers are advantaged from -36 dB to -56 dB of loss. Within that loss frame, a redriver should be considered because of the lower systems costs and ease of installation. In large, high-loss, high-impairment systems, retimers are advantaged. Oftentimes, either redrivers or retimers could possibly work in a system. Retimers can offer more insurance against unforeseen performance impacts, but redrivers can be proven to work well in testing, so most customers would prefer to use it in applicable cases. Overall, redrivers offer lower systems costs and ease of installation over retimers. Additionally, once you are certain of your system loss, you can leverage IBIS AMI models developed by TI to perform simulations on high-speed serial links. Many of our redrivers have IBIS AMI models pre-created that can be used to provide current voltage output curves, rising-falling transition waveforms, and see package parasitics. With an IBIS AMI model, it is a lot easier to determine whether our redriver will be able to compensate for the loss in your system. So, it is recommended to simulate before you design. To obtain these models, make a post on the Engineer to Engineer forum, or E2E, or check the TI website of the device you are interested in. To alleviate the system loss, a TI PCIe redriver was used to boost the signal transmission. The EQ boost and corresponding EQ index ensured that the bit transitions were properly amplified. Retimers and redrivers are the most commonly used form of signal conditioning, and there are certain loss cases where redrivers are better and others where retimers are better. Check out our available redrivers and use IBIS AMI models downloadable from ti.com to start simulating today. As you can see, we offer a wide portfolio between PCIe Gen 1 all the way to PCIe Gen 5 of different channel count and different lane count of muxes, redrivers, and retimers up to Gen 4. If you're interested in any of the products listed in the table on the slide, please search for their name on ti.com. Thank you.